So today we are happy to have Andrei Barnachev from Trinity College Dublin, and he's going to tell us about heavy states, black holes, bootstrap, and holography.
Thank you. Right. Um, So, yeah, it's good.
Yeah, it's
Might be.
a little tough for people.
I think there's a preset.
Yeah. Oh,
You can go to one of the presets. This, that preset is find an image.
Is this the one?
probably. Yeah, that
Yeah.
looks pretty good.
Sort of
You look like the
Those presets not very good.
Yeah. This looks good.
Okay, bless you. Okay, so, what are we talking about? Maybe my story. From a field theory. The large sample chart. And, first, once we do the first call, what much? So that is the suggestion where it is very. There are really two parts. There is some technical work that is work here, but I want to get to result. There will be two types of results. One is more mathematical, has to do with near light algebra, near light construction, near light and the second thing, which is sort of disjoint from it, is the situation where I'll look at the slide operator will be taken to the system, comes every and I'll analyze it in some program model, and there will be some lesson for AMAX average volume condition. Also, no for cases of conformal. So again, this is more, I would say, I don't know, mathematical, not mathematical. This is more about structures, right structures, and this is more like physics application, a little bit required. So this correlator can also be used in variety other ways. But I'm not going to go. But let me just mention a couple of interesting situations where they can use. One is type stabilization. That is to say, if I consider a heavy state in a CFD, is it the same as thermal state? And for what I'm going to say, I'll just assume it's the case. There are a few things that you can say about this, but if you're interested, you can discuss it afterwards. Thermalization. And the second thing I'm not going to talk about is energy scattering or acorn scattering, where you consider scattering particles, gravity, and you can ask the question, black holes for what agenda. So this is double charge. 50, a C. Double charge of 50. Large 50. Okay, so that's a plan. Let me start. And first, the holography. Prime example of RCC is holographic CFDs with extra conditions of smart spectrum, these sorts of things, or just so let's just start with Einstein, right? And then what we're going to say relates to Einstein, right? That of course is a safety to know this condition. Now, this part is slightly more subtle. So the most so let me start by reminding you that if we have a program and we can do it from this diagram, which describes the solution of graviton to the four-point function. Then this diagram scales of 1 squared and or 1 over C or 1 over C, where C is a proportion to C. And the natural question is how to decompose this in terms of problem. So it's just 1 or 1 yeah, yeah. So what do we decompose it in terms of? Well, since the graviton change, you may think that the first answer is one contribution. This one term that comes here is so we want to decompose it from the blocks where 1, 1, O, and 2, 2, O are the one big addition, and D after the bar is the little block. Let's say the bar are the cross ratio, and they just tell you where, let's say, operator O1 the solution of infinity with one operator 0, one operator 1. Let's say this one is 1, this one is infinity, and this guy according to which are two independent coordinates, and then the rest is okay. We map with open function, basically boils down. Now, as I said, one contribution is present, so one term is under 1, 1 T. Let me I'm going to normalize all operators to one running this sum. So, of course, the word identity, the big addition to the first answer is just 1 minus 0. The big addition to this guy is 1 over 0. So, indeed, the first number. So now you see immediately that this term is still one. So 15 means the combo block of the first number. However, there are other things. This component. So these are contributions from double bracket operators. That's the 1, 1. The same from double bracket operators made out of it. The big addition, this would be good. Yeah, like 1. this is the scale like 1/15. So you see the whole of that scale like 1/15. So this is how you can work this diagram. And of course, since the diagram in principle, with the fish, for example, formula for all this application. Now, the last question, what happens if we consider Hamilton? Yeah.
How do you extract the chart? You basically know all of these fees as well, basically.
Yeah, well, these are just normal blocks. So they all know. Yeah, so how I do this? Addition, basically no limits. But now you ask the question, what happens if you like this? Which is the blue diagram. Because this diagram is one of the past, this one, the diagram is given. But you can make a bigger other than by taking the total dimension of your torque rate. So let me take a torque rate heavy, which I mean by H here. Let me square beta H to the other. In this case, again, this vertex gets the factor of delta A squared. And this let me also introduce important parameter, which is just the ratio of delta H. I keep writing C because that's what matches what we're running with. Yes, C again is a simple charge. So, mu is what I'm doing. So this is the same as 1 over n squared times squared. So diagram for the new. Now we see that making one heavy allows us to keep a subset of diagrams. Then the diagram. So we just keep some blue diagrams, but of course the distance of this let me also write down how when we consider all educated correlator that diagram and this diagram are expanded in the normal block. So this is the same formula. If I consider so if or two of heavy, then what happens is first number term, new term, and this term comes delta was the C and delta heavy is the C. So delta heavy is delta C and delta heavy over C is new because delta heavy. This diagram comes with spectral view, and this diagram again can try to decompose into the contribution of very separated from the blocks. So here, the main contribution will come from the double spectrum, which basically corresponds to having the gradient, is an operator that involves two spectrums and that structure. Second, but the important thing is that so this application came like delta over C. This application gets like delta H squared C. So the whole diagram scales like delta times mu squared. Now the difference between this and this is going to be 15. So there's only one criteria which is linear in speed, which is in itself, but there are instances many primary operators made out of two. So infinite many operators, which I denote here as infinite. So if I kill that, I mean it's infinite many operators. Why are there infinite many? Because I can insert derivative. So simplest operator is just T between the job. Then I can put in this. This is simple. Then I can contract a couple of indices. Even though this is true. And everything zero. But in addition, I can start adding things. I can make prime operator this time. The alpha, beta, and I can also add blocks. So that infinite domain object. And in the following, I'm going to be talking about the class of the operators, which is still infinite domain, but it's a class of them. There will be operators of minimum.
So there's no sense of the highest the ones that express.
Look the other way around. It's a lot of them. So focus on operator into the K operators minimal case. Which remind you is just the normal function math. So that means that we don't contract any forces and we don't introduce any forces. We don't take any derivatives and we don't introduce any forces. So for example, here I think the delta, the alpha beta, the mu delta, this is operators. And for the mention, they will all be visible. Why do I want to do it? Because these are going to be operators that will give the limit distribution in the near horizon, in the near line. This is just a statement that if you consider not B of two operators, both sides 0, or sum x in x in L, O in L, x squared. So this is the usual for B, but for operators with B. So what appears here is reasonable. This is just a statement. The near light cone of B is dominated by operators with the small c. That's the operator. Okay, so now a little bit of philosophy. It's a fairly easy exercise to check this limit that I'm considering, large C, large delta area which scale to C, and mu corresponds to the black hole area. That's what the operator the property is not to. This is the statement that the black hole metric is minus squared plus r squared plus r squared one, where d is the spacing function, and f is 1 plus r squared minus mu times r to b minus 2 of r. So this is just the usual ADS black hole metric, and mu is related to the mass of the black hole, and this d minus 2 over L1, d minus 1 times mu. So if we want to ask what is the conformal dimension, the operator that corresponds to the black hole We just need to multiply by the radius. Multiply by the radius. R d minus 1 over L prime d minus 1 is 2D. Numbers of 2 times. Now you see that the formal motion of the black hole is precisely the same check that field. So these are the objects. Okay. So from the photographic point of view, what I'm going to do when I'm discussing heavy like correlates is I'm going to consider black hole from BS, and I will look at correlators, like correlators, boundary. So I will look at like correlators of two like operators. Practice compute these correlators by just computing two conjunctions like operators in a black hole, which is the exercise, problem with this exercise. However, if you did this, then you can try to use the ODE to read off this ODE coefficient. And people managed to read off the QOD coefficient. And actually, this is something that hopefully I will talk about where we use the stress test. But so the point is that if you do it, it's perfect. You cannot go there. Yeah, well, some people did just, that's the part of it. But that's a very good starting point, but you cannot go very far. Well, statement is that the principle we can actually compute the whole correlate by using the okay, so correct.
So the reason you're not, so all these multi-key things are some kind of multi-gravitronics.
Yeah.
So and why are you not interested in the single gravitronics?
No, because it's bigger. I mean, a single gradient exchange, plus single stress tensor and only one operator, plus a double operator. So, but yeah. So I would say that in the following, I was interested in the stress tensor effect, which are operators of this type. E is where the compute is brought. As I said, there are other operators. I'm going to forget along.
You won't have to keep them as fractal out.
Well, basically, well, so you can ask, why? So there are a few answers. One answer is that there are variables which are instant. And the second answer to the question is, we're not talking about the TT correlator, the multiple status are the same as the double trace operator made out of the double pair. So they'll be included. So let me just go. All right. So let me remind you what happens in two dimensions. The two dimensions is of course the Zora algebra, and the stress tensor factor of heavy light operator is known as the Raptor vacuum. So it's just made out of Raptor descendant identity. And it's small, exactly small. So when D equals 2, the Raptor, everything is exactly known. Heavy light operator. Demonstrates it as a form, it's the delta curly F, where curly F can be expanded in positive mu is the same as before. And this turns out to be mu times F2, where F2, Fa is polarization here, but A is equal to 2 to the power A, represents A, and A. So F is good enough. number, two squared plus another number, times one plus two, plus another number, times that's where the light. Oh, this is the, this is the, oh, this is light break, some light break.
But not necessarily, not necessarily.
No. So, and Q, one, so the interesting point in this structure is that here, the cosine square only terms that involve couple of F's in this term, such that the subscript sum to 4. Here, only terms that involve 3x, such that the subscript sum to 6. So let me say F1, F1, F4. So we know that the structure of this into C is very rich. The F, so this one will be. So why is that? But we also, in addition, the scalar F satisfies following equation. So these are where F equals mu 1 times T plus U times U. Non-linear differential, which is the product of this known, you get the set of the line. All of this is known. Now, what's interesting is if you look at the log curve, this guy, so consider log curve. E of mu, I call the coefficient of the log E of mu, log 1 of 3. So if you substitute it in here, you get algebraic equation, which is E equals mu plus E squared. Solution is something like 1 minus square root 1 minus 4 mu. So is a generating function of for capital numbers. So far, it's just an amazing function. But solution turns out to be generating function of capital numbers. One way to describe capital numbers, many ways to describe capital numbers. One way is described as the number of linear extensions of partial order cells. Of this type. So there are 4 elements. This is catalog number 2. This is catalog number 3. So what do I mean by that? By that I mean partially ordered set with 4 elements, such that this is smaller than this, is smaller than this is smaller than this, and this is smaller than this. So it's like Young block. So numbers always supposed to go up this way and this way. The same here. This is smaller than this, smaller than this, smaller than this. So how many ways do I have to totally order this stuff? This is the number of linear extension. So this stuff is 2. So I can put 1, 2, 3, 4, or I can put 1, 3, 2, 4. So both of this complete ordering satisfy the diagram. This turns out to be 5 and 12. Notice the fact that these are capital numbers, and they happen to form this generating function, which happens in satisfying this equation. That we knew it, you could get the whole thing. So this is all 2.
This is only sensitive.
Oh yeah, because
If I add, so if I added like, extra light.
it's just that there are sort of so that identity there are sort of so it's only a contribution of the adjustment.
That means because you have to try that.
Yeah.
That's what could have more. So,
It is the fact of life that if you look at this result, consider it on this cylinder. Then what we and on the cylinder, of course, the two function of life operated as the average. It's an interesting fact that this thing like this. But once you go beyond that, you might need to consider.
So why does it going to get? If I think that the rabbit was a black hole back then, and I use my two light operators.
Yeah. Good. You get the stop pressure. So that question is happens to be the answer. You get this plus double pressure. Now take the limit of the black hole when it goes to the multiplier pressure. Make it into cylinder. Then all the double pressure pressure. So that's what that means.
Is there a way to make sense of like the fact that mu actually less than one, that like an extreme black hole?
Yeah, so that's actually good. So that actually is a good question. So because this is all really quantum singularities is coming, but you can go to larger universe, then you get measurement now. You then you get. If you really want to see a black hole, consider a large universe. Look at some threats. Look at I that.
So a geometric origin to this equation like that.
I'd love to know what happens in the testing animals.
Large C, there's like a geodesic.
Yeah, but doesn't apply. If this computation will apply to large delta line. So that computation you can do and you get this result, but it's limited to large delta. Now, there's another way of computing this thing. So this thing honestly will compute it by just looking at the Schur algebra and basically if I brute force getting this equation something. There are other ways that I'm aware of and compute it. Not the one very much. But anyway, it might be worth thinking. So what happens in 40? In 40, it turns out that if you consider GMI, I will just tell you that if
Was there recently mentioned this, was that definition of Hadron number?
yeah, mental problem. So in 40, I'll just tell you the answer. Let me just say that you can compute it by doing the burden. So the structure is very similar. And no, the same story happens in any given number of dimensions. I have a red light in this form. The plan takes this form, where now F as we knew and F3. This is just electron tilde, or the tilde is mu times C bar, where C bar is the Laplace coordinate which I take to 0 to make sure I only keep the living light cone operating at each tower. So only, as I said, I only want to keep the living light cone. So take C bar to 0, which is the fix. So this make sure I keep the living twist of the stanzas, but they still probably construct. So this is just a light cone limit of the stratum. And there is an infinity square. If I have 3 square plus F1 F5 plus 4 square. So numbers here which possibly can help us. Now you see the structure is exactly the same. Well, sorry. As in 2D, just look at 3, and here something that sums to 6, substitutes step 2 and something step 4, and so on. So all of this is known, these numbers. I'm not going to write them down. I just mention all of them. Not the, well, actually, well, Right. Right. Right.
You have your story.
That's right. Exactly. So, now, let me, I promise to mention this, the analogs of cattle numbers. Let me just mention here that in certain limit, we look at the log term, just as we look into dimension. This guy turns out to be generating number of linear extensions of the following process. They're almost like partially ordered sets for catalog, but they just have one extra point in the middle. So catalog at this point is this. This guy is this point is this, so it's slightly different kind of flow. So if you count this guy, you will get a number from the if you count this guy, get a number from the square, and so on. So if we knew how to write down an equation for this generating function, we would be in much better shape because I suspect we'd be able to solve it. As of now, we can't solve it. Don't know the full solution. We can just solve it all the better. But if we knew it, maybe we could solve it.
But what's the connection between, this is probably trying to solve and
Oh, that's what the physics problem came down. Just in two dimensions.
sorry, it didn't come down to that. It came down to some function 1 minus or 1 minus 4u.
In two dimensions.
Okay, yeah.
But
But,
could also say,
once you wrote down that function, nowhere did the counting problem appear in the derivation of that.
good. So, yeah, so in 2D, well, well, okay, so there is a way to, there is connection which is still a bit technical, but maybe it's a bit better than what I just described. And that involves a number of binary trees. So in 2D, this problem of diagonalizing the null persistent state boils down to studying binary trees. The number of binary trees happens to be a cattle number as well. So this connection sort of more than that. Here, you could say that if you had some kind of effective description of four-dimensional grid on your left, something like this would happen. We don't know. Now, let me just mention that if you study W3 algebra in two dimensions, so now instead of studying Virasoro, study W3 algebra. Have you like works in W3 algebra? No, just like that Virasoro. They have exactly the same form as heavy letter correlated. Exactly the same form with the three the numbers. And for that problem, again, there is a counting. You count not a number of binary trees, but you count the number of trees which possibly trigger with couple of triggers. Unfortunately, we're not aware of the generalization of that story to the public. Then there are other direct connections to the story. So for example, I probably don't have time to go into it. But you can try to, let me just say a few words about if we're interested in stuff. Because I want to go to the second part. So what happens is you can try to, in the Virasoro case, when you compute commutative generators, just compute this is a standard story of computing integral this kind of integer, then you use LBE, and then you get the central charge. This. Plus this integer as well. And then it's important, this term, actually both Holger as well are important. Because this term is important. Who is a heterogeneity function? You can get it from that central charge term. F3 you can get from the central charge term of W3. So you can try to play this same kind of games with the lighter dimensional CFT. And you sort of get the first term. Then, yeah, there are issues which at the moment. So I don't get too much into detail here because the issues are resolved. I want to switch to I want to talk about the second part, but something interesting. Okay. So probably have a question. Well, generally it's d minus, it's d over 2 plus 1. The common factor is increased. Well, beyond what I just said. I mean, this kind of generator is well, I don't know. I mean, we don't know that. But try to make a generator of this type, try to ignore all the divergences, then the kind of structure to get is like that's one. Okay, so part two. Part two is actually more physics. So it involves studying computing a TT correlator in the black hole background. Maybe yes, and again doing the oblique stuff. Turns out that there are quite many to come up. So let me just make some general statements. So I compute the TT correlator in computing it in thermal background, same as computing at state. So I need to compute this kind of correlator. So generally, there's an identity contribution. The identity contribution just gives me the vacuum result. So this is TT vacuum result. Then there is a contribution of the stress tensor, and I'm going to talk about creative field. So the only contributions I'm going to get are contributions of identity, stress tensor, multiple tensors. Stress tensor, new, let me just put the tilde on it so that you normalize it's easier to count the big coefficient. So this is a big coefficient. But to see, you may check. This just follows from the fact that PTT feels like C, so the tilde need to divide it. This guy, as we discussed before, is delta heavy over C. So this whole thing is like C, is like delta heavy, is the same as C times mu. Mu scales like 10 to the 4. So this is C times C times 4. This is the usual connected term in the two-point function of stress tensor. Now, multi-stress tensor, let's discuss double stress tensor. So this guy, as we discussed before, is delta heavy squared of C. And this guy turns out to be C. So this whole contribution scales like delta heavy squared or C squared times mu. So this response to this connect. So I need to conclude that these squared. Yeah. I need to include correction, which will give me contribution to connect. So plus P, where this will be my connected correlator, and this connected correlator is affected by the normal dimension without square. So it's there, and it's going to feed into the next. Now we just do the holographic population, do the expansion, and rid of all the data, the total line, particularly we release the anomalous dimension of the double separator. Negative, true, so everything works. Now there's a question, what if you consider not Einstein filter, but I'm not going back to the question, but Einstein filter gravity with the delta level. So well, 1 over 16 by G, with the G, R, number, L squared, plus number goes from there, L squared times the equivalent of the. This is the delta level. Okay. So then we can do the same exercise. And we find something in. Well, first of all, let me remind you that that's not the correlators by temperature.
Can you remind me that the E4 term splits A from C?
So and you may ask, well, we know that those gravity is non-unitary. However, non-unitarity issues appear in different geometric issues. That's the one way. So now let me remind you about the two-dimensional pattern that has three independent polarization. So let me consider one polarization. Consider actually something which is integrated to the function. Integral y, t, alpha beta, x, t, gamma delta, so 0. This is my correlator. So this is therefore G of the theta gamma delta. And there are three independent points. That's y, and txt, and tt. Let's just discuss one polarization. This is the story of the same. So consider gxy. So first of all, there's x expanded in your case. There's a vacuum result, which is c and x plus to x minus 2. Where x plus, x minor, is usual p plus 9. So that's not dependent on p and c. So this is the vacuum result. Then there is something which is proportional to temperature before. So the kinematic form, or what is proportional to temperature force, is x plus squared plus x minus squared with numbers known divided by x plus squared x minus. And then there is another term which is proportional to temperature to the base. So there is some stuff which starts with x plus 2 here and log x minus. This is the fraction. Now I'm interested in the near light condition. I take x minus 2. So in this near light condition, this term is irrelevant. This term is also relevant. And then for certain value of the Gaussian Nyquist, this term just meant you can ask what is the value of the Gaussian. This is the value where conformal collided bound. Let me remind you that conformal collided bound also known as ANET is a statement that if you make custom state and measure T naught I and I in it, which is the energy time. then this object must be greater than. It has been proven actually using a variety of ways, but in CFT, it can prove it. So it's a fact of life that this bound true, they lead to linear relation on the three couplings we discussed. Remind you that the TCP correlator determines that three couplings. So when one of these linear relations saturated, we say that conformal collider that bound is saturated.
But in that case, we expect that the CFT has a free component, so it will be very far from Einstein gravity.
Good. So it is indeed true that free sphere is saturated. Now, it is also true that Gauss-Bonnet sphere is saturated from a collider bound to a certain relative. And this, of course, happens precisely when this coefficient vanishes. So this is zero when corresponding n from a collider bound is saturated. This by itself is not at all surprising because this term comes from the TDT of it. And so the in fact this term comes from the living with term, the TDT of E. It's not surprising that it's governed by the corresponding n. It's not at all surprising that this bound saturated. In fact, people know this because of gravity that when you saturate bound, the TT correlator, graviton becomes superluminous. So all this is not present at this stage. What is surprising is that the next term also this term is also exactly the same value. That is the statement that the highest container is saturated. So then you ask the question, what happens to how the terms? Turns out that they're all saturated. So saturation of this into n leads to saturation of in 4 and 6 all highest containers. The whole correlator in the near left minute allows us to back and forth. Now, so in a sense, the theory is. So, however, it's also creating this channel. In particular, if you look at the two-point function in other polarization, if you saturate this particular angle, remember there are three angles. If you saturate this angle, only this guy becomes vacuum. The other two will not. The theory, in a way, is free, but only in the second. So that's the. Now, the question is, how general is it? Because we say, well, that's the net, right? Well, first of all, that's the net. Unitary, that was an issue. They claim that non-unitarity issue appears in the other issue. In this. You say, well, still, let's see. However, this zero would be true for all fields. So from here, principle to learn the lesson for all fields. The question is, how much of the lesson can we learn from the fact that all has saturated in the command plants into it? So that's that I think. Yes, I'm ready to summarize. So
But I mean, that's unclear that there is a single
that's
which that happens. That's a total.
Yeah.
Yeah, it's not that yes, that you have no good.
so
So yeah, but you think that there is a non-release for which the first thing is zero, then it's guaranteed that the rest of them is zero? Or
Well,
that is not.
that's a good question. I'm not sure. Why do you think that I think it's large? Or this might be a statement that you are done with machine all the systems of physics. So larger than maybe the But that's,
And remind me, you also said that on the reviews of not income.
yeah, this year is not done. This year. Other temperature to the floor will be dominated by this two. This year, the double system operator will not be able to do.
I thought that. Lining was. You can have it, but you need to have it, make it unitary, you need to have, light higher spin field,
Right.
so are those light higher spin fields?
No, so, well, yes, we do. We need to have, a basket field, that's another question, what is the, where is the entire field? Why is this? And, one thing to start this question is to look at the CT of take it to the direction. That's how basically it is proved with this ecosystem. Take it to the direction. And then, if you take the light on limit, then the main contribution comes from the first answer, and you end up with some of the weather. If you take the opposite limit version, then this whole version is rejected. And then you see how the non-linearity breaks down, and you need the final test. So that's how it works. But the point is that the normal collider bond is in the opposite from the regime where A equals C condition is important. So that's basically what I meant by saying that the entire issue of this theory is different from there than what they expect.
I guess I thought that more coefficient, you'll need to have some higher spin, like higher spin fields involved, and won't they contribute to the thermal PT?
Yeah, no, look, it's something the same question. So, but the question is why you need interested in better, but that the entire thing happens from in other words, you could have said, well, the theory is not durable, just throw it away. Then, well, how come it knows about the original level? So, for certain question, the theory is bad, but for questions of this type, it's actually. So, okay, so the summary, for two parts. First part of trying to show how structures, the near-left limited curvatures look very similar to W3 algebra and W10 algebra structure, but don't hear the kind of answer to is there an algebra government near-left table? Or is there a nice theory or question? That answer is not. Although something going on. The second part, there is this physics question, which is what happens if you start with PT correlates in the and if you saturate this model, saturate in Gladbach whole orbit velocity back and forth. So it's interesting to, but first of all, the slide of the back of the forward to left hand side is one question is how to connect it to the first part of the story. Second is how general the statement it's not any although you can try to play with, from the capital, people visit, but this AOC, from what I know, can primarily for the other one, but never get close to pressure. Nice, that was where. Get close to pressure. Well, more generous. Is that relevant to real world physics? So, these are the questions. Thank you very much.
But the other was some, replacement like this. Right, the bone, 100% replacement. Okay.
And then maybe, yeah, I don't know. Well, actually,
In 3 dimensions, they are saturated outside of.
yeah,
Yeah.
Yeah.
What, you mean that,
Those theories are kind of.
Well, they are.
They want the speculation. So,
These are the matter. Matter, transparency.